right, if you have not done so yet, pause it, try it for yourself, and then come back here when you are ready for the solution. The car initially has a speed of 20 meters per second. It's nice when they word it like that. That tells us exactly what this is. It's our initial speed. I'm going to rewrite give the guess right here. So we know the initial velocity equals 20 meters per second. And I'm going to not use units, just to save some space. If the car needs to reach 30 meters per second at the top of the ramp, 30 meters per second at the top, so it looks like we're driving up this ramp and we need to get to 30 meters per second right here up at the top. That means our final velocity will be 30 meters per second. And the ramp is 200 meters long, so this is all 200 meters. We're going to call that x equals 200 meters. What acceleration must the car have to reach the necessary speed? So that would make our unknown the acceleration. And our equation, v naught, vf, x, a, we don't have time, so we're going to use the equation without time, v naught squared plus 2a delta x. Vf squared is going to be 400. V naught squared, whoa! Vf squared is 30 squared, so 900 equals 400 plus 2a times 200. 2 times 200 is 400. 400 subtracted from each side, we have 500 over 400 equals a. That should give us an acceleration of 1.25 meters per second squared, always showing your units. Let me clean this up. Car initially moving at 40 meters per second, about 90 miles an hour. So they're speeding. 40 meters per second. Initially moving, so there it is again. Initial velocity equals 40 meters per second. Sees an officer up ahead and slows down. That'll avoid the ticket. Slows down over a period of 10 seconds. With an acceleration of magnitude 3 meters per second. How far does the car, meter per second squared, how far does the car move during this time? How far? That means we're looking for a distance. So what equation are we going to use? Well, we have v naught t a x. How about that displacement formula? X equals x naught plus v naught t plus 1/2 a t squared. It's already set up. Our initial position is 0, so that'll just go away. Initial velocity is 40. Plug that in. 40 times 10 is 400. Plus half of a, so 1.5 times t squared, which is 100. 1.5 times 100 is going to be 150. So we have x equals 550. That's the right answer, right? Oh, it's not, is it? So what happened? So we have to think about, and here's where the physics is going to come into play. We have to think about what is actually happening in this scenario. So the car is moving forward. It's speeding along and then sees a police officer, so it slows down. If we are going in this direction, what direction does our acceleration have to be going? Opposite. So we're dealing with a negative acceleration here. So this is how important it is to go through and be very careful about putting in your correct signs. Now the problem did offer a hint when it said, oh, it's a magnitude of 3 meters per second squared. So you wanted to just put in 3 meters per second squared. But that changes things because now all of this is negative. And now it is 400 minus 150 to give us 250 meters. And I led you down that path just to make the point of you have to really understand what's going on in the problem. If you need to draw a picture, please draw a picture. Right now, it's kind of like, yeah, stuff moving along the x-axis. No big deal. It'll get significantly more difficult rather quickly. So it's okay to get in the habit of just sketching something out. I had a student tell me today that they were struggling with something conceptually, and then as soon as I drew it, they said, oh, I understand now. So please, it does work. That sounds like a made-up story, but it's not.